Hi folks, welcome back. And what we should have looked at previously is two other probability distributions. Those were binomial and Poisson. So when we looked at them, they were specific to problems which had what we call discrete outcomes. An example we looked at is taxis turning up at a taxi rank, so there could be 3, 4, 5, or 6. That was in Poisson, because we didn't have an upper limit there. Or when we looked at binomial, we did have a fixed upper limit, but again, we were looking at games of pinball, so these were discrete, i.e. countable, 1 to 10. So what happens if the data is not discrete? And so we're talking about things like length, height, weight, temperature even. So just to illustrate this, what we've got here is a child, and at 5 years old, the height was taken to be about 0.56 metres. And then again, 10-year-olds, their measure and their height was found to be about 1.27 metres. So we're going from 0.56 to 1.27 between 5 years and 10 years. Okay, here's the question. What height were they when they were aged 8 years and 3 months? Well, that looks as if it lies in the range 5 to 10 years. So you would think that maybe the height would range between 0.56 metres and 1.27 metres. So here's a little, well, it's not quite a metre stick, it's more than that, maybe a 2-metre stick. And it looks like we've got there 5 years is marked at 0.56 metres and 10 years at 1.26 metres. Is that what it was? So we were asking the question, what height were they at 8 years and 3 months? So some people are thinking, well, did they grow continuously? And some people have heard, oh, they took a spurt in height at 7 years. So, but it would probably be somewhere within that range, hopefully. Okay, so going from 5 years up to 10 years, we don't know, but see that arrow there? It looks as if it can take on all possible values. So it's not jumping from 0.56 to 0.7 to 0.8, 0.9, 0.6. Okay, it looks as if it's taking on a continuum of values, an infinite number of values. Right. Okay, so I'm just trying to get the point here that we're not dealing with discrete countable data. 1 egg, 2 egg, 3 eggs, etc. But yet again, it does all depend on your measuring instruments. Technically, or mathematically speaking, there's an infinite number of values. But you know, your meter stick or 2-meter stick or gauge, whatever it is, it can only go to a certain degree of accuracy. So we'll bear that in mind. Okay, so normal distribution probability formula. Right, okay. There, that's very scary. And so for us here, we've got little numbers on that big fancy kind of stretched out S sign. That's involving a topic known as calculus or integration, and it's used to actually calculate areas. So actually that is what we're going to use this. So for us, throughout this, areas and probabilities are equivalent. Okay, so the things that we're interested in here in this formula are two things. We've come across mu as a mean arithmetic average. We've come across that before. But the other thing there, that little letter, that refers to the standard deviation, and that's just the spread of values either side of the mean. And we'll talk about that later. And you should have read the basic statistics notes and exercises, but you should be familiar with them. Okay. We are not going to have to calculate standard deviation here, but that little letter there, that's one of the Greek letters, and that's referred to as sigma. So that's what we're going to use it, and it's lowercase sigma or wee sigma. And they like sigma within probability and statistics. So there, you might have seen that before. That's actually uppercase sigma or big sigma. That means in that one there is usually used to add up or to sum up. And if you look at the basic statistics, notes and standard deviation, you'll see it. Okay, let's just look at a little example here. Well, it's not an example, it's an illustration of the graph of the heights of 1,000 females. Okay, there we go. So on the left hand side, I've just put frequency or number. I'm not putting 1,000 up there. Okay, the 1,000 will actually be all the bars that are illustrated in the graph there. So it looks as if it might peak up about 200. Okay, so we're starting at 1.4 meters by the looks of it, going up to about 2.2 meters. Okay, and so you might expect maybe very few at 1.4. Then as you increase in height, you might expect to start middling out there. Okay, and then as you approach 2.2, maybe very few. Okay, oh yeah, I forgot to put in the units. Better late than never, put in the meters. But this kind of shape here, where you have a kind of middling value, so it looks, that kind of the highest bar there, that looks as if it's peaking just below 200, so maybe 180 or so. So that's in 180 of the females. They look as if they're taking on a middling value of 1.7. Okay, so here, what I've done there, I've just tried to envelop that kind of bar chart, and we've got this kind of very familiar curve, and it appears a lot of times in various scenarios. So that there, they refer to that as a bell curve. Some people think it looks like a bell, or sometimes I like to call it the normal curve. Right, okay. There we go. Got another version of the normal curve. Since we're dealing with probabilities, we've seen before that whatever the scenario, the situation, the probabilities, that they always add up regardless to give you 1. Always, always, always. Okay, so we're stressing that. Again, going back to the normal curve, and there's a little formula it's going to give us for probabilities where are actually areas under that curve. So you can see back to that formula there. Underneath the summation sign, we're taking on values. It goes from somewhere called negative infinity up to x. So on the graph, that's why we're actually starting at a place called negative infinity. It doesn't really exist, but very, very, very large, small negative number. Okay, so that's why I've got negative infinity to the left of the graph, and the area under the curve there will be infinitesimally small. As you can see, the graph's almost touching that horizontal axis. So we're starting with the x being very small, and as we increase it, you can actually see that the area is increasing. So here we go, it's going along there, and there, that's a kind of middling point there. So that means that the shaded part that area would be 0.5, okay, which equates to a probability of 0.5. And as we make x bigger, we just keep going, all the way till it almost fills up the curve, okay? And that x, it just goes on forever to positive infinity. And you'll never achieve that value, okay? Never achieve it. What you're talking about here, we're probably going to go up to about 3.6, something like that, 3.7. And now in both directions, either side of the mean. Right. Okay, so let's talk about the bell curve. And so here, it's going to get a bit complicated in a diagram, so I took this from my exercises. And so here, just talk about this normal curve and certain aspects of it. So they say it's got a symmetric bell shape either side of the mean. Okay, that's what it's showing you there. The mean and the median. The median's just your kind of centrally placed value in a data set, going from smallest to biggest or vice versa. And they're usually located at centre if our data is normally distributed. Also, sometimes the mode will be equal to the mean and the median, but you don't always have a mode like a most popular value, especially if your data is continuous. Okay, you can't put a finger on values that appear the most often because that's what the mode is. So here, what I'm saying, one standard deviation either side of the centre when the graph is the mean. What you get approximately 2/3 of that data falls in that region. Right, so 68% they're saying approximately. Just think 2/3 because that's about 66.666. So if we move out from the mean and go 2 standard deviations either side, what you've actually got there is 95% of the data falling within 2 standard deviations of the centre where the mean is located. And if you move out just a little bit further to 3 standard deviations either side, you've got 99.7%. So you're only losing 0.3% of the data of the area. So that's what the 0.15% extreme left and extreme right represent. And you've only went out 3 standard deviations and you've almost got the entire area under the bell curve. So basically, that means you've virtually got all of the probabilities. So that's what these areas are, the probabilities. Okay, so there's the normal curve again, and we're just stressing this time and time again, it's that area. Okay, it's not the x values going along the axis. They are just connected to the areas, and that area is a probability. Here, so put a line down the middle, that's where your mean would be located. So that area there is exactly 0.5. Okay, then what they do is they change an x into a z. And so we'll be calculating things called z scores. Right, that's just to confuse you. So don't worry about that. We'll get there. So put the 0 there on the horizontal axis, right in the centre. That's our mean. And up the top there, directly above the 0, that just means we are going to record the area that depends on z, our z score, that we'll talk about later. So there's the mean is 0. Okay. And again, they're telling you that area A dependent on Z. That's what A bracket Z close bracket mean. A depends on Z. Right, and the way we're going to calculate it, that's why I showed you half the table there. we're only going to use positive values coming away from the mean at 0. So that table there, our Z values, once we've calculated them, right, that's, so here, hopefully you can see that there. There you go, that's our Z values there, right, and we start at 0, okay, and as we go down, you can see the values are getting bigger, 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 and bigger. But what I want to show you here, I'm just going to scroll down the page here and show you that the sort of the thing I'm referring to is the Z values on the table that we are using here. They're only gone up to 3.6. Well, that would be actually 3.69 because you get 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I started at 0.0, so that's actually 0.8. So the corresponding area there, if you can see it, is 0.4999. Don't quite achieve 0.5. We'll never achieve 0.5. So for us, that's the table that we're going to be using to calculate these areas, which relate to probabilities. Okay, so once we've got our Z value, we go to the table, and the Z is related to the area. The Z score is not the area of probability. So starting at 0 there, you don't have any area. So as you increase 0, and that's not the Wizard of Oz there, we're just increasing Z. So we're going away to the right from 0. And as we do that, you can see the area under the curve. So that's A of Z, which depends on. So as Z increases, that area will increase. And because we've only got half the curve, technically you would get to 0.5, but we'll never get to 0.5. And that Z, it just goes on forever. Okay, to a place called infinity, which we'll never reach. Okay, and like we just showed you there, there's a table that we're going to use, and as I highlighted earlier, it only goes up to 0.4999 right down the bottom corner. Okay, so if we have negative values for a Z-score, we just turn it into a positive value because the curve is actually symmetric. So you'll see later, probably look at an example like that. So initially, we're going to go and find how to use the table from a calculated Z-score, and we'll do that later. So I'm just picking this. Let's go and get the area, actually, that relates to a value of 0.23, right? So 0.2, that's our first decimal place. So if we go to our table there, and that's actually pretty small, so I'm just going to magnify that there, and I went down, so I went down this column here, and that'll give me my first decimal place, and I've actually just stopped at 0.2 there, right? And I've highlighted the entire row there. That's something I'm interested in, the entire row. Okay. Then once we've got the entire row highlighted, we need to go to the second decimal place. So I think we had 0.23. So we're going to go for there next. And we're going to go down the entire column. And where the row and column intersect, that's our area, which is our probability. Okay, so it's the area coming away from 0 to the right. There you go. I can see that's 0.0910 or just 0.091. And I've just blown it up so we can see it clearly. So that, for us in our problems, that is a probability. And there you go. There's your wee little area coming away from the right from 0, but that's our probability. It's not the 0.23, it's the 0.091. Just less, 10%, 9%. Okay. Okay, you try and find 0.15. So you might want to pause there and see how you get on. So 0.15, so we want to get the table out and go to 0.1 first of all and locate that column. Then secondly, we'll go and find 5 in the second decimal place. So we go along the top to 0.05. Right, but here's the table. So 0.1, so we'll go down underneath Z. Then we'll get 0.1. We're going to highlight the entire row. And our second decimal place was a 5, so I've highlighted it, and come down from there, highlight the entire column. And the intersection, so from a Z value of 0.15, our area probability is 0.0596. And again, I've just highlighted it, just so we can all see it. Okay, so hopefully we can master the table. Right, and there you go. So from 0 up to Z, onto the bell curve, highlighted in sort of light blue there, that's our area or probability. And there's the table, and you've actually got these tables in a 6-page document. It actually goes through pointing out how you select areas of interest in your probability problems. Okay, so it looks as if we're going to get a question here. Okay, some university are looking for applicants, successful applicants who maybe do well an exam will be allowed entry. But the thing is here, all they're telling you is that the mean score is 500 with a standard deviation of 100. So going back to standard deviation, if you look 100 either side, going from 400 to 600, so that means there's about 68% of the students within that range. Okay, let's move forward. But to gain entry, an applicant must score more than 70% of all the other applicants. It doesn't say they have this past a certain score. It's they need to get past 70% of all the others. Okay, that's what we're saying here. Okay, so this applicant scores 585. Right, so we're hoping that score is greater than 70% of the others. Well, the applicant's hoping that. Right, so let's see how we go through this there. So the things that are highlighted there, the mean, standard deviation, and the 585, that's going to be our X value. So here's the situation here. That's for a bell curve, that's the mean 500, standard deviation of 100, and that's the score of interest 585. Okay. So line down the middle, that's going to be the mean, 500. Where's 585? Well, it looks as if it's to the right. So maybe initially that looks good. But is that past 70% of other applicants? We don't know. That's what we're going to find out. So there's the mean. So what we're doing here is normalizing the curve. So whatever the mean is, in regards to the table, it will take the value of 0. And then we'll normalize the 585. Okay, so that's what we're going to be doing there. So we need to find a z-score that will give us that area that's highlighted in blue for us. Right. Okay. Here's our z-score. And it just depends on those 3 values. Our x value, our mean and standard deviation. Here's a little formula to work them out. So it's the difference between our x value and the mean. all divided by the standard deviation, sigma. Put your three numbers in. Value at the top, 85 over 100, and what comes out is a nice decimal. So that there, the Z value, that's where you would go to the table, 0.85, and that will give you the related area, which is a probability. Okay, 0.85. So if I went down to 0.8, highlighted the entire row, and I'm going to only go to 0.5, okay, up the top there, and the intersection between row and column is our area or probability. That looks like 0.3023. Okay, I'm fine with that. So Z equals 0.85. We're saying the probability that depended on that Z value there. From the table we got 0.3023. Right. That is an area or a probability. We keep stressing that. Anyway, the bell curve, or the area enveloped by the bell curve and above the horizontal axis, that's all of the students. We don't know how many there is. We don't need to know. All we need to know is hopefully that line there is bigger than 70%. That's all we're sort of looking at here. So coming away from 0 to our Z value effectively, that's our probability. I'm going to call that P1 because you'll see in a little minute we're going to have another probability. So from the table, that's how we got the 0.3023. That's our probability highlighted coming away from 0. Right, and to the left of that, that's actually 0.5 because that's half of the bell curve. That's going to come into the problem as well. Right, because we need that. We need to go all the way from there up to the right of P1. So we're hoping that P1 and P2 will exceed 70%. So that's where we're going with this problem here. Because the entire area is 100% or 1. So we're hoping that P1 plus P2 is greater than 70%. Because that's where our applicant is lying, to the right of P1. Okay, we can see P1 is 0.3023. P2 is 0.5. We've seen that earlier. Okay, so that total probability there is the sum of them, sum of P1 and P2. We'll just add them together and come up with 0.8023. So what's 0.8023? And I think we can just about sneak that in there. I'll just make it into a percentage because we're going to compare that to the 70%. Well, that looks good. 80%. That's looking good for our applicant. So the applicant, because actually they got just a little bit over 80%, but the thing is, it's a lot more than 70%. So that means in this problem, they will get admitted onto the course. So I think I'm going to finish that one there because it's a bit lengthy. But remember, just rewind it at any time. And so this will be normal distribution video part 1. And we'll put up another one because we're getting on for half an hour there. That's quite long. But there's a lot of explanation here. So just the most important part is to go and find the areas of interest. So practice from the other exercise booklet. That's what that is directed at, to assist you in that task. Right, so I'm going to end there, and that means I'll be able to go on and just go over our second video.